Okay, so have you ever had that feeling like deep learning just works?
It can feel like magic, right?
Yeah, like you've got these models, more parameters than data points, and they still generalize somehow.
You see these crazy things. Error rates going down, then spiking up, then down again as the models grow.
It's like, what is going on in that black box?
Yeah, if you've ever wondered, how is this even possible? You are definitely not alone.
And you know what's really fascinating? The research we're diving into today, it's suggesting that these seemingly super modern mysteries, they might actually have explanations, like rooted in pretty well-established theories.
Absolutely. For a while now, these phenomena, we're talking overparametrization, double descent.
Even models perfectly fitting noisy data, but still generalizing.
Right. It's led to this perception that deep learning is playing by a different set of rules.
Like our old understanding of generalization. Just chuck it out the window.
Yeah, like the textbooks are obsolete.
But our mission today, to really dig into a different perspective.
One that argues these things, they're not actually unique to neural networks.
And they can be understood through frameworks we already have.
Existing generalization frameworks.
Exactly. There's this whole idea floating around, go rewrite the textbooks to account for this stuff.
But what if we're looking at it wrong?
What if the textbooks were right all along?
More insightful than we gave them credit for.
And that's what we're looking at today, this argument that maybe, just maybe, they were onto something. So we're going to be exploring this paper. It's called Deep Learning is Not So Mysterious or Different. And along with that, my own notes trying to decode this thing.
Sounds good.
And our goal, not just to skim the surface, we want to go a bit deeper, like give you a more academically grounded, knowledge-rich understanding of what's going on here.
I like it. Let's get academic.
So to start, let's lay out those mysteries themselves.
All right, the mysteries.
The things that have fueled this perception that deep learning is fundamentally different.
Yeah, what are the key phenomena that have made people think, whoa, something weird is happening here?
What might you have seen as a listener that made you go, hold on a second, this doesn't seem right?
Right.
Okay, let's unpack this a bit. So the big three that keep cropping up are overparametrization.
Yeah, overparametrization, that's a big one.
Double descent.
And benign overfitting.
Benign overfitting, yeah. Overparametrization is probably the one that's most baffling, intuitively.
I'd agree with that.
You've got these massive neural networks, way more parameters than data points.
Huge models.
And somehow they don't just memorize everything. They actually generalize to new data, stuff they'd never seen before. It's like, how is that even possible?
Right, you'd think they'd just memorize the training set and call it a day.
Exactly. But they don't. And the fascinating thing is, this paper we're looking at, it suggests this isn't some new anomaly. It's something our older theories might have already predicted. Just needed the right perspective, the right lens to see it. Then we have double descent. So typically you'd think as your model gets more complex,
More parameters, more layers.
your test error will go down at first.
Right, because it's getting better at fitting the data.
But then it'll start going up again. That's the classic bias variance trade-off, right?
Exactly.
But in deep learning, we see this weird pattern. It dips, it spikes, then it dips again as we make the models bigger.
Like it gets worse than magically better just by adding more neurons.
It's like, what?
And here's where things get really interesting. This isn't necessarily new. It's not just a deep learning thing. We've seen it in other areas of machine learning as well.
Right. It feels like the model's going against everything we thought we knew. Like, how can making it more complex make it generalize better? It's counterintuitive.
Right.
And then finally, we have benign overfitting. This is where a model, it could fit perfectly even to totally random noise.
Zero training error. Perfect fit.
But then it still performs okay on the actual structured data. It's like it's overfitting and generalizing at the same time.
Seems like a contradiction, right?
Total contradiction.
It's one of those things that made people really scratch their heads.
Yeah, like, is everything we know wrong?
Exactly. But the central claim of this research, these things, they aren't exclusive to deep learning.
They're not just a big learning party.
The paper argues that you can actually observe similar behaviors in much similar models as well. So the question becomes, what is it about these deep learning models? What allows them to do these seemingly strange things?
Without breaking the fundamental principles of learning.
Right.
And this brings us to the idea of soft inductive biases. We hear about inductive biases all the time. These assumptions baked into a learning algorithm, they help it prioritize certain hypotheses over others.
Yeah, like giving the model a little nudge in the right direction.
So what's the difference between the traditional view of these biases and this soft perspective?
And how does it help us understand all this craziness better?
Yeah.
All right, so traditionally we think of inductive biases as restriction biases. They're like hard constraints. Think of the architecture of a convolutional neural network, a CNN. The convolutional layers, the pooling layers, those are hard constraints on what the model can learn.
They force the model to look for certain types of patterns.
Exactly. They impose assumptions like locality, translation invariance. So for image data, for example, they shrink the space of possible solutions. The model can only consider functions that fit those constraints.
So it's like saying, we're only going to look at models that have this particular structure.
Exactly. But this paper, it argues that these hard constraints, these restriction biases, they're not strictly necessary.
And in some cases, they might actually be a bad thing.
Yeah, they could prevent the model from learning some subtle aspects of the data.
Things that don't fit neatly into those hard constraints.
Right, and that's where soft inductive biases come into play. So instead of outright rejecting certain solutions, soft biases express a preference. Some solutions are better than others, but it's all within a much more flexible hypothesis space.
So it's more like a nudge than a hard stop sign.
Exactly.
Okay, can you give us some concrete examples of these soft inductive biases, something we can really wrap our heads around?
Absolutely. One great example, and the paper uses this a lot, is order-dependent regularization in polynomials.
Polynomials, okay.
So imagine you're fitting a curve to some data points. You could use a low-order polynomial. That's like a restriction bias. You're limiting the model's complexity from the get-go.
Right.
But you could also use a very high-order polynomial. Give the model a ton of flexibility.
But then what? It'll just overfit like crazy.
Well, that's where the soft bias comes in. You penalize those higher-order terms. You add a cost to using them.
So the model can use them if it absolutely needs to, but it'd rather not.
Exactly. And the paper actually has this great figure, figure 1 at the top. They show how a 150th order polynomial with this kind of regularization can fit simple data with a simple curve. But it can also fit more complex data with a more complex curve. And it can even fit pure noise. By wiggling all over the place, it uses those high order terms, but only because it has to.
So it's like saying, go ahead, be complex if you must, but we're going to make you pay for it.
Right.
What about neural networks? How do soft biases show up there?
Well, a classic example is weight decay, also known as L2 regularization.
Oh yeah, weight decay. I've heard of that.
So it adds a penalty to the sum of the squared weights in the network.
Okay.
And this has the effect of pushing the network towards solutions with smaller weights.
Smaller weights.
Yeah, and smaller weights often correspond to simpler functions, which tend to generalize better.
So it's not that the model can't have large weights, but it's sort of nudged towards keeping them small.
Exactly. It's a gentle encouragement to find a simpler explanation that still fits the data. The paper also talks about how residual pathway priors can turn those hard architectural constraints we talked about earlier, like in CNNs, into soft biases.
So instead of strictly enforcing a certain way of connecting things in the network, there's just a preference for it.
Right. The network can deviate if it needs to.
So it's leaning towards that structure, but it has some wiggle room.
Exactly. And the important thing to remember here is that these soft biases, they let us have these really flexible hypothesis spaces, like models that can represent a wide range of functions.
But without necessarily going crazy with overfitting.
Right, because there's this underlying preference for simpler explanations.
Okay, that makes sense. And the paper actually has a couple of figures that illustrate this idea really well.
Figures 3 and 4.
They show how a soft preference can guide you through this massive space of potential solutions. It's like having a map, but not a set of strict directions.
I like that analogy.
All right, so now let's talk about the generalization frameworks themselves. You mentioned that some of the traditional ones kind of struggle with these deep learning mysteries.
Yeah, they don't always handle them gracefully.
Which ones are we talking about, and why do they fall short?
So frameworks like VC dimension and Rademacher complexity, they're super important. They're foundational to learning theory, but they tend to give us these loose bounds, especially when you're dealing with large overparametrized models.
Yeah, they're not very helpful in practice when your model has a gazillion parameters.
Right. So VC dimension, it measures how well a hypothesis space can shatter data points. Essentially, how many points a model can perfectly classify no matter how you label them.
Okay,
And for neural networks with lox parameters, the VC dimension can be really high,
which means?
which means the generalization bounds it gives you, they're not very informative. They might suggest the model will overfit terribly, but in practice, it might generalize just fine.
Interesting.
Then there's Rademacher complexity. It measures how well a model can fit random noise.
Nice. Okay.
And this can be a problem, especially with things like benign overfitting, where the model can fit noise perfectly.
But it still does well on the actual structured data.
Right. Rademacher complexity might say the model will generalize poorly, but that's not the whole story. The problem is that these frameworks often focus on the size or complexity of the entire hypothesis space. They don't really care about the specific hypothesis that the model actually learns.
So it's like measuring the size of the whole toolbox. But what we really care about is the quality of the specific wrench we used.
Exactly.
So what are some frameworks that actually work better for deep learning?
The paper highlights PAC-Bayes and countable hypothesis bounds as really promising approaches.
Okay, PAC-Bayes, countable hypothesis bounds. Those are the cool kids on the block, huh?
They're definitely gaining traction. They offer a different way of thinking about generalization.
So how are they different?
Well, instead of just looking at the capacity of the entire model class, these frameworks consider the likelihood of specific hypotheses within that class. They often incorporate prior beliefs.
So it's less about the potential of the model overall and more about how plausible the specific explanation it came up with is.
Precisely. Let's look at the countable hypothesis bound. It's laid out in Theorem 3.1 in Equation 1 of the paper. It gives us an upper bound on the expected risk, which is what we care about, how well the model will perform on new data.
Right.
And it's based on the empirical risk, how well it did on the training data, plus a term that depends on the prior probability of the chosen hypothesis. We write that as pH, where H is the hypothesis.
So how likely that particular hypothesis is even before seeing the data?
Exactly. And this a prior acts as a weighting function. It favors some hypotheses over others.
So a model that prefers simpler explanations would have a higher pH under a prior that favors simplicity.
Exactly. And the cool thing is, we can use any prior we want to evaluate the bound. It doesn't have to be the prior that the learning algorithm actually used.
So if we believe the model has a bias towards simplicity, we can use a simplicity favoring prior to get a tighter bound.
Exactly. And this ties in beautifully with the idea of Kolmogorov complexity. It's mentioned in equation 2.
Kolmogorov complexity, that's a mouthful.
I know, right? It's a measure of how complex something is, essentially, how many bits of information you need to describe it.
Okay.
And the Solomonov prior, it suggests that the probability of a hypothesis is related to its Kolmogorov complexity. Simpler hypotheses, the ones that can be described with fewer bits, they get a higher prior weight.
So even if you have a huge model, if it learns parameters that represent a simple explanation, the generalization bound can still be good.
Precisely.
That's pretty cool. What about PAC-Bayes? How does that fit into all of this?
So PAC-Bayes takes things a step further. Instead of just considering a single hypothesis, it looks at a distribution over possible solutions.
A whole distribution.
Yeah, it's written as Q. So instead of asking how likely a specific hypothesis is under a prior, it looks at the difference between this posterior distribution Q and the prior.
Okay.
And that difference is measured by something called the Kullback-Leibler divergence. We write it as KLQP.
KL divergence.
It's a way of measuring how much the data has changed our beliefs.
From the prior to the posterior.
Right. And by considering a whole distribution of solutions, PAC-Bayes can sometimes give us even tighter bounds. And the paper actually points out a really interesting connection here. Even a PAC-Bayes bound with a single hypothesis, a point mass posterior, can recover something similar to the countable hypothesis bound.
Interesting.
And they also highlight the link between marginal likelihood, which is a key idea in Bayesian inference, and these PAC-Bayes bounds.
Marginal likely, that's essentially the evidence for a model, right?
Exactly. It tells you how well the model explains the data overall.
So these frameworks, they're not just theoretical toys. The paper talks about how they're being applied to real deep learning models, even the really big ones like LLMs, and they're getting surprisingly good results.
Yeah, they mention examples like Lotfi et al. 2022a. They got pretty good bounds on the classification error for CFAR10 using PAC-Bayes.
So they're not just playing around with equations. These frameworks have real-world implications.
Exactly.
All right, so we have these frameworks that don't just penalize the size of the model, they care about the plausibility of the solution it found. How do these frameworks help us understand those mysteries we talked about earlier? Let's start with benign overfitting.
All right, benign overfitting. So this is where the model perfectly fits the noisy data, but still generalizes reasonably well. The old intuition, based on those traditional frameworks we talked about, would say this is a recipe for disaster.
Yeah, just memorizing the noise.
But with PAC-Bayes and countable hypothesis bounds, it's different. It's about whether the model has a prior preference for simple explanations. Even if it can wiggle around to fit every noisy data point, if it prefers smoother, simpler functions.
The generalization bound can still be good.
Exactly. The prior acts as a filter even when the model has a ton of parameters.
So it's like the model is saying, I could tell you a really complicated story that perfectly explains all the data, even the noise. But I'm going to tell you a simpler story instead.
Exactly. It's looking for the most elegant explanation. And the paper actually uses that polynomial example again to illustrate this. The high-order polynomial with the regularization, it can fit noisy data perfectly. But because it prefers those lower-order terms, it's still generalized okay.
Because it's not putting too much weight on those high-order terms that are just fitting the noise.
Right. They also talk about Gaussian processes, GPs. They can fit noisy labels perfectly, but they still generalize reasonably well. And the marginal likelihood, which is related to those PAC-Bayes bounds, it goes down as you add more noisy labels.
So the Bayesian framework is essentially penalizing the model for coming up with more and more complex explanations to account for the noise.
It's like Occam's razor in action. The simplest explanation is usually the best. And the paper points out that benign overfitting isn't just a deep learning thing. We've seen it in simpler models, like linear regression.
Really?
Yeah, and importantly, they mention that these new frameworks, PAC-Bayes and countable hypothesis bounds, they pass this rethinking generalization test.
What's that?
It was proposed by Zhang et al. Back in 2021. It's a way of testing whether a framework can tell the difference between learning on natural data and learning on random data. And these frameworks, they pass the test.
So they're capturing something real, something fundamental about generalization.
Exactly.
Okay, so benign overfitting is starting to make a bit more sense. What about overparametrization itself? Is it still weird that these huge models work so well?
The paper argues that it shouldn't be, especially when you consider these modern generalization frameworks and the idea of soft biases.
Okay.
They point out that even before deep learning was a thing, in Bayesian methods, it was common to use models with more parameters than data points.
More parameters than data points. That's like the definition of overparametrization.
Right, but it can work. Gaussian processes are a great example. They can be seen as having infinitely many parameters, but they have a strong simplicity bias, and they often perform really well.
So having lots of parameters isn't inherently bad. It's about whether the model is being pushed towards simpler solutions within that huge space of possibilities.
Exactly. And the paper actually points out something really interesting. Increasing the number of parameters can actually have two positive effects.
Two, I thought it was just one, more flexibility.
Well, yes, it does give you more flexibility. The model can represent a wider range of functions, but it can also increase something called a compression bias.
Compression bias, huh?
It's the tendency for larger models to be stored with less memory after training. It's like they're finding more efficient ways to represent the information.
So it's not just about having more room to move around, it's about finding more compact solutions within that space.
Exactly. There's some really interesting research on this. Maddox et al. In 2020 found that larger models often have lower effective dimensionality after training, meaning fewer of their parameters are really important for the solution. Goldblum et al. In 2024 showed that larger language models generate sequences with lower Kolmogorov complexity. So even though they have more parameters, they're actually finding simpler explanations.
It's counterintuitive, but it makes sense. The extra capacity gives the model more room to breathe to find those elegant, compressed representations.
Exactly. And the paper suggests that larger models might prefer these flatter solutions. Regions in the loss landscape where small changes to the parameters don't affect the loss much. These flat solutions tend to generalize better. They also mention Bartlett et al. From 2020, who found that overparametrized models often converge to solutions with small norms, which can be seen as simpler.
Okay?
And one more interesting point they bring up, the implicit biases of the optimization algorithms we use, things like stochastic gradient descent, they're often credited as a key reason why deep learning generalizes so well.
Right.
But this paper suggests that maybe they're not the main driver. Maybe it's just that there are so many good solutions in that vast parameter space that the model is almost guaranteed to find one.
So it's less about the specific path the optimization algorithm takes, and more about the landscape itself having lots of good spots to land in.
Exactly. And that suggests that the architecture of the model, combined with those soft biases, might be more important than the specific optimization algorithm you use.
That's a pretty big claim, but it fits with this whole idea that more parameters isn't necessarily a bad thing, as long as there's something guiding the model towards simpler solutions.
Right.
Okay, let's tackle the last mystery, double descent. That one still feels a bit magical to me.
Yeah, that dip-spake-dip pattern.
How can these frameworks help us understand that?
So double descent, it's where the test error goes down, then up, then down again as the model gets more complex.
Right.
It seems strange at first, but the paper points out that this isn't new at all.
It's not.
Nope. We saw it in simpler models way back in the 80s and 90s. Belkin et al. Brought it back into the spotlight in 2019, and they showed it happening in random forests and random feature models, too.
So it's not just a deep learning quirk.
Nope. And the explanation for that second descent, where more complexity leads to better generalization, it has to do with moving from an underparametrized regime to an overparametrized one, specifically an interpreting regime where the model can perfectly fit all the training data.
Okay.
So initially, as you add parameters, the model gets better at capturing the patterns in the data.
The first descent.
Right. But as you get close to being able to perfectly fit the data, adding more parameters can lead to overfitting. You start fitting the noise and generalization gets worse.
That's the spike.
But then, as you keep adding parameters even more,
Beyond the point of perfect fitting.
something interesting happens. The number of good solutions or flat solutions in the loss landscape, it starts to increase.
So even though the model's getting more complex, it's finding these simpler, more stable solutions.
Exactly. And in this highly overparametrized regime, the effective dimensionality of the solutions actually goes down. Even though you have more parameters, fewer of them are really determining the solution.
It's like the signals being spread out across more parameters.
Exactly, and that makes the model more robust. The paper uses a simple linear model example to illustrate this. As you increase the number of features, the signal gets diluted across more and more parameters.
And the simplest solution, the one with the smallest norm, it actually becomes simpler in a way.
Right, they also show double descent happening in both a ResNet 18 and a linear model. And it's really cool to see how the effective dimensionality tracks that second descent.
It's not magic, it's just geometry.
And they even show that PAC-Bayes bounds can track this phenomenon too. Larger models become more compressible in that second descent regime.
Okay, so it seems like this idea of simplicity with inflexibility, which is enabled by those soft inductive biases, it really ties all these mysteries together.
I think so too. It's a really elegant way of looking at it.
But if deep learning isn't so different in terms of these core principles, what does make it stand out? The paper touches on that towards the end.
Yeah, they acknowledge that deep learning does have some unique and powerful features. One of the big ones is representation learning.
Okay, representation learning.
Most traditional models, they use a fixed set of basis functions. They map the input data into some feature space. But neural networks, they learn these basis functions from the data itself.
So the model is learning how to look at the data in the most useful way for the task at hand.
Exactly. The weights of the network, they control the shape of these basis functions.
It's like the model is building its own set of lenses to view the data through.
I like that. It's like it's learning its own feature extractor.
And that's really important for high-dimensional data, right? Like images and text, where those standard ways of measuring similarity just don't work very well.
Right, because pixels that are close together might not actually be semantically related. But a neural network can learn to represent those pixels in a way that captures the underlying meaning. They give an example in the paper about predicting the orientation of a face. Faces with similar orientations might have very different pixel values, but a well-trained neural network can learn to represent them in a similar way.
So it's not just about having a flexible model, it's about having a model that learns how to be flexible in the most useful way.
Exactly. The paper also mentions deep kernel learning as a way to kind of bridge the gap between kernel methods and neural networks. It's a really interesting area.
Cool. What's the second distinctive feature?
The second one is universal learning.
Universal learning. Okay.
So traditionally, machine learning has been all about specialized models. You pick the right model for the right task, no free lunch theorem and all that.
Right.
But deep learning, especially with the rise of transformers, it seems to be breaking that rule.
We're seeing these more general purpose models that work well across a wide range of tasks.
Exactly. And the paper suggests that this might be because both neural networks and natural data, they have a bias towards low Kolmogorov complexity.
So they're both, in a sense, simple.
In a way, yeah. And that shared simplicity bias might be what allows these models to generalize so well across different domains. Think about LLMs. They can do all sorts of crazy things, even tasks they weren't specifically trained for. Like in-context learning is a great example. You can give an LLM a few examples of a new task, and it can often figure out how to do it without any explicit training.
It's like they're learning to learn.
Exactly. The paper even draws an analogy between a pre-trained transformer and a mixture of GP experts. It's like it has this whole toolbox of different kernels, and it can select the right ones for the task at hand.
That's wild. So what's the third distinctive aspect?
The third one is mode connectivity.
Mode connectivity.
So you've got these different neural networks. They're trained independently on the same data, and they might converge to different solutions, different local optima in the loss landscape.
Right.
But what's surprising is that these different solutions, they're often connected by these simple paths in the loss landscape.
Paths where the loss stays low.
Exactly. And this is pretty weird. It suggests that the loss landscape isn't as bumpy and disconnected as we thought.
Not like rolling hills than jagged peaks.
Yeah, more like that. And this has implications for generalization. It also suggests that there might be even better solutions out there that we haven't found yet.
Because we're just getting stuck in the local optima.
Right, and this has led to some interesting new optimization techniques. Things like stochastic weight averaging, SWA, and model merging, where you essentially combine different solutions to get an even better one.
So it's like taking the best of both worlds.
Exactly. Now, the paper does point out that mode connectivity might not be totally unique to neural networks, but it's definitely a prominent phenomenon in deep learning, probably because their loss landscapes are so complex and high-dimensional.
Okay, so the fundamental principles of generalization might apply more broadly than we thought. But deep learning still has some tricks up its sleeve, especially when it comes to representation learning, its ability to generalize across different tasks, and the way its solutions are connected in the loss landscape.
That
So what's the big takeaway from all of this?
I think the main message of the paper is that overparametrization, benign overfitting, and double descent. They're all interesting, for sure, but they don't necessarily mean we need to throw out everything we know about generalization.
It's not a revolution, it's more of an evolution.
Exactly. It's more about understanding how these powerful new models are using those old principles in new and interesting ways.
It's like they're taking the best of both worlds, the flexibility of large models combined with the wisdom of these classic theoretical frameworks,
I like that. And the paper encourages people to dive deeper into the research they cite for those who really want to get into the mathematical nitty-gritty.
which we definitely encourage.
Absolutely.
So for you, the listener, the mystery of deep learning generalization, maybe it's not about breaking the old rules, but about understanding how these models are bending them, using them to their advantage.
And maybe, just maybe, it's telling us something deeper about the nature of learning itself.
Ooh, that's a good one. That's something to ponder.
It is. And as always, we encourage you to share your thoughts and questions with us. We'd love to hear what you think.
Absolutely. Thanks for joining us on this deep dive.
It's been a pleasure.
Until next time.
See you then.